Today, we're going to talk about a force that's, well, it's shaping pretty much everything around us, from gigantic bridges all the way down to the tiny circuits in your phone. We're going to do that by digging into this really fascinating document from 1949 from the National Bureau of Standards to get our heads around the science of thermal expansion.
You've probably wondered about this at some point, right? Why do bridges have those big metal-toothed gaps? And what's with that iconic click-clack sound of a train on the tracks? Well, the answer isn't just about how they're built. No, it's about a fundamental property of matter that engineers have to wrestle with every single day.
Okay, so to get to the bottom of those clicking tracks and gapped bridges, we've got to understand the science at the heart of it all. So let's just start with the big question: what exactly is thermal expansion? To put it simply, it's the fact that almost everything changes size when it heats up or cools down. See, when you heat something, you're basically pumping its atoms full of energy. They start vibrating like crazy, pushing each other apart, and just taking up more space. So the whole object gets bigger. And you guessed it, the opposite happens when things get cold. But here's a wrinkle. Not everything expands in a nice, neat, uniform way. As you can see here, there's a really key distinction. You have isotropic materials, like a simple block of metal, that expand equally in all directions. But then you have anisotropic materials. Think of a piece of wood. It's going to expand way more along the grain than it does against it. And that's a super critical detail for anyone who's trying to build something. So here's the thing. These changes are often absolutely tiny. We're talking microscopic. A huge steel beam might only expand by a few millimeters over its entire length. So how on earth did scientists back in 1949 measure these little, almost imperceptible changes with any kind of accuracy? Well, they built these incredible machines, like the one you're looking at right now. This is the precision micrometric apparatus. And yeah, it might look like something out of an old sci-fi movie, but this was totally state-of-the-art. This was the tool for measuring the thermal expansion of solids with just amazing accuracy. The method itself is actually quite brilliant. So you take a sample rod and you heat it up in a furnace. Then, hanging from each end, you have these incredibly fine wires. I mean, sometimes just 1/1000th of an inch in diameter. And then you get two powerful microscopes to measure the tiniest change in the distance between those wires. It's a simple idea, really, but wow, it must have required incredible precision to actually pull it off. But that micrometric method, that was just one way to do it. Scientists came up with some truly clever ways to see the unseeable. They were using everything from light itself to the then brand new technology of X-rays. So just imagine trying to measure something with a ruler that's made of light. That's pretty much the core idea behind what's called the Fizeau interferometer method. It's this amazing optical technique that can measure changes far, far smaller than the width of a human hair.
Now here's the brilliant part. You take a tiny sample and you put it between two ultra-flat quartz plates. You shine a single color light through them, and what you see are these light and dark bands. They call them interference fringes. So as the sample heats up and expands, it pushes those plates apart, which makes the fringes drift across your view. All the scientists had to do was count how many fringes moved past a little reference mark, and from that they could calculate the expansion with just mind-boggling accuracy.
But what if you wanted to see what's happening at the most fundamental level, the level of the atoms themselves? Well, for that, scientists in the early 20th century turned to a brand new, powerful tool: X-rays. This method is just so clever. You shoot X-rays at a crystal, and you can measure the exact distance between the layers of atoms in its structure. Then, as the crystal gets hotter, those atomic layers actually move further apart. So by measuring that change, you're not just measuring the expansion of the object, you're literally measuring the expansion of the atomic lattice itself. It's incredible. Okay, so measuring this stuff is one thing, but this whole phenomenon isn't just some scientific curiosity. Understanding thermal expansion lets us turn what could be a really destructive problem into a brilliant solution.
And a perfect example of this is the thermostat in your house. The main part, this thing called a bimetallic strip, is just brilliantly simple. You see, it's two different metals with very different expansion rates, and they're bonded together. When it gets hot, the metal that expands more forces the whole strip to bend. That simple, predictable motion is all you need to make or break an electrical contact, which is what turns your furnace or your air conditioner on and off.
So as scientists gathered all this data, they started looking for deeper patterns. They weren't just asking how much things expand, but why. Were there some underlying laws that governed this whole behavior? And yep, they found some really fascinating relationships. Take a look at this chart from that 1949 circular. It's plotting an element's expansion rate against its melting point. And you can see this really distinct inverse curve. Elements with super high melting points, like tungsten way up here, they have very low rates of expansion. And then elements with low melting points, like potassium down at the bottom, they expand a lot. This shows a deep, deep connection between how strongly atoms are bonded together and how they respond to heat. You know, this quote from the source material really just says it all. From the tiny, precise gears in a watch to massive suspension bridges, from casting molten metal in a foundry to designing the circuits in our electronics, understanding and accounting for thermal expansion is just absolutely essential. So the next time you hear your house creak on a really hot day, or you see those expansion joints in a sidewalk, you'll know exactly what's happening. It's a little reminder that even the most solid-seeming objects are in this constant, invisible dance with temperature, stretching and shrinking in a world that is always, always in motion. Makes you wonder, what other unseen forces are at play all around us?